session, we'll just have one overview about a speed mode or a torque mode in electric vehicles, and mostly we'll look the speed or torque mode for PMSM or the BLDC motors. As all we know nowadays, for electric two-wheelers or everywhere, the PMSM and BLDC motors are very common and widely used. Also, for these motors are AC motors, and for these motors, the very famous and well-known technique for its control is the field-oriented control, or shortly we'll call it as a FOC. This is also it is efficient, and because it is very efficient compared to others, this becomes very popular in industry. And nowadays, efficiency is one of the key factors in electric vehicles. If you go ahead, then this particular architecture defines the FOC control. You can see this is FOC control in a torque mode. So we'll consider that we are getting a torque request from the acceleration pedal. If it is a four-wheeler, you will have that acceleration pedal in the at the leg, and if you are driving a two-wheeler, you will have in form of a throttle that is in hand. So we are getting those acceleration inputs from those respective acceleration pedal or throttle, and this will defines the actual torque which we require, and this actual torque will be coming ahead with the major, let me consider this IQ as a torque which is a proportional torque from the motor, and then after we have the PI controller, and through the PI controller it is converting into by doing the Clark transformation, and we are getting the voltage VA, VB and VC. At the input of this Clark transformation, we can have that VQ at this PI and VD at the end of this PI. This VD and VQ are converted into VA, VB, VC. And then those VA, VBC, as those are in analog form, this VA, VB and VC, those will be converted into PWM pulses, or we call it as a space vector PWM. So let's consider that this particular space vector PWM converts this analog form of voltage into respective PWM signals, and those PWM signals will be provided to the gate of the inverter. As an inverter will have the IGBTs or the MOSFETs, and which is driven by the gate, and those gates PWM signals will be controlled by this SU PWM, and indirectly it is controlled by the voltage generated at the end of this transformation. And then finally the three-phase AC motor will realize the voltage applied to the motor. Same way, we have the input at here, three-phase VA, IA, IB, IC, which we need to convert into respect to ID and IQ. So for that purpose, we need to do a transformation which converts the ABC frame of reference to DQ frame of reference, and same the inverse transformation which converts the DQ frame of reference to ABC frame of reference. Before going ahead into FOC control, we need to understand what exactly this DQ frame of reference and ABC frame of reference. ABC frame of reference is very obvious, that we already know the three-phase motor will be driven by ABC, so that's why those three phases are represented by VA, VB, VC. But what is this DQ frame of reference? So to understand that, let's assume a case that you are on a track, a railway station, and you are standing on a platform. Then there is a one person who is inside a train, and the train is moving with a constant speed. then you will see that that person is also moving with a constant speed as that of a train from the route. Now, then when you enter into the train, then you will see that previously the person who was going with a constant speed, if you are inside a train, you will see that that person is having a constant. The position is a constant. It is not moving now. He becomes a stationary. But when you entered into the train, that means if you change your location from platform to train, you will see the perspective or the motion in the different form. When you are platform, then you saw the person inside the train is moving with this particular speed as a train, and when you move inside the train, then you saw that particular person is just stationary with respect to you. Now let's same concept we will put over here. Let's assume that you are on the stator. Now let's, our thing is here, we consider that the PMSM BLDC motor is rotor is at the center, rotor is rotating, and the stator, which is the outer part of the motor, which is fixed. This is not rotating, right? So that is a basic thing that I'm assuming that you all know. So if you are on a stator, then you saw the rotor is rotating with a particular speed. So rotor how it rotates? It starts from zero angle. If you take a particular point and it will start from zero angle, it will move to 90, then in 180, then 270, then 360, and it repeats. So the rotor is rotating its all angles repetitively, right? And if rotor is rotating repetitively with some particular frequency, there is also a current which moves from the stator, and as you know already, there is a rotating magnetic field in the stator which cause the rotor to rotate with a particular speed. So as you increase the rotating magnetic field of the stator, the respective, you will observe the rotor's rotating speed also will increase. That rotor's rotating magnetic field is the result of the rotor current, that is these are AC motors, so the current are rotating with a particular frequency. So this is like, as we are dealing with a PMSM motor, there is a slight difference in PMSM and BLDC, but right now we're not going into that. We just want to restrict ourselves to this. So let's assume that, one more assumption, that we are exciting our motor with sinusoidal voltage, and the same way we will observe the current generated in the motor is also sinusoidal in nature. So let's have this particular current sinusoidal in nature with a particular frequency, and we also saw previously our rotor is rotating also with a particular frequency, and these are proportional. So as the rotating, the frequency of a current increase, then the rotor's speed also will increase. So there is a relation that Ns is equal to 120 F upon P. That is I not written over here, but that is the relation. Ns is the synchronous speed. Let's consider that the speed at this is the synchronous motor. Our rotor is rotating with the fixed speed, that is Ns, and that particular rotating speed is equal to 120 F upon P. P is number of poles. Right now forget about that. So this equation will talk the rotor speed is proportional to F, that is the frequency of the current. As the current frequency increase, the rotor speed also will increase. Now let's link a previous example of the train. Now suppose you are on a stator. Now look, this all situation that's rotating rotor and oscillating current nature, this is all we have saw when we are sitting on the stator. Now let's jump onto the rotor. When you jump onto the rotor, what will be the situation? Here the situation will come that once you are on a rotor, then with respect to you, the rotor will be stationary, right? Because you are also rotating with the rotor. So once you feel is rotor is stationary, then you will see all parameters become constants and not in oscillatory nature on the frequency, right? And that is, just imagine, just compare our previous example of a train with here right now. On stator, all terms are oscillating. Your voltage, your current, your rotor, all are oscillating. But once you jump on the rotor, sorry, on stator, everything is oscillating with particular frequency. But as you jump on the rotor's motion becomes stationary because you are also rotating with the same speed of the rotor. So as the rotor's terms are stationary, we also see the current, voltage, all terminology becomes stationary. How? As I said earlier, 120 F upon P NS. So it's proportional, right? So frequency increase, this frequency also increase. So both are proportional. So now as the rotor speed is constant, the rotor's oscillating frequency is a constant, then the stator's current, that current oscillating term also also become constant when you look from the rotor's perspective. Okay, that's all we saw. We compared the train example and we got the term all are constants. Why? But why need to do that? Why need to change our frame of reference from stator to rotor? Is there any specific need, or it's just to make our system complicated? Not like that. There is a very, very, very significant thing that we have to take care or we should know. If we are controlling the oscillating terms or oscillating behavior, then it is very difficult to control. It's not that easy to control. And it is also proved mathematically that if you are going to track something oscillating and something vibrant, it's very difficult. But if you are going to track which is not oscillating, which is constant, then it is easy to control, right? So that's why from control terminology, when you are controlling something, it is always prefer that your terminologies which are involved in the controls should be constant in nature. Then you will be controlling it very accurately, nicely, precisely, right? So that's why for AC motors, we are converting those AC waveform or AC behavior into the DC behavior, and that will be possible when you change the frame of reference from stator to rotor, right? So I think you understood the importance of change of frame of reference from stator to rotor. With this background, if we go ahead, then we will see the frame of reference. There is a need of frame of reference, change of frame of reference, and why it is important, so much important, right? I'm not going into dwell into like mathematical parts which is shown over here, but I'm just explaining so to understand very properly the just idea what is the beauty of this one. So for that reason, what are the motors frame of reference, that ABC frame of reference, with the help of those Clark-Park transformation, we are converted into DQ frame of reference. Okay. Now we have that DQ frame of reference. So in that frame of reference, the one term is ID and another term is IQ. So ID term, in our case, is represents uh, the term which dealing with the flux. In case of BLDC motor or PMSM motor, we are having the magnet as the rotor. So normally the ID term, we need a reference ID term as 0. In this particular session, I will keep this as assumption and I will explain why ID need to be 0 in some later discussion. I will better say we will be doing some discussions. And this IQ term is correspondingly represents the proportional term of torque. So this will represents the equal. IQ represents the torque and ID represents the field term over here. So as the field is already excited by the magnets, so the field component from the stator current we want to be 0. So we'll putting reference for ID reference is 0, ID reference as a 0. So from these transformations, we need after the transformation ID to be regulated to 0, and IQ, this we want to be regulated to the respective torque which is received from the acceleration pedal or the throttle. Right now I'm just considering that you already know the behavior of a PI and how PI works. Then what are the difference comes from here, that going through the PI, this will generate VQ, this will generate VD. So to maintain our ID 0, what VD required, that will be calculated, and to get that particular torque, how much VQ required, that will be received over here. So this IQ represents the equivalent term of the torque which will be responsible for the speed. So over here you can see that directly we have a torque as a reference. ID reference we are always making at 0. There are some special conditions where ID could be negative, but right now we will limit ourselves that ID reference we are keeping as a 0, and then we are applying the torque which is received from acceleration pedal or throttle, and those reference values, it is comparing their difference, error is calculated and their error given to the PI, and the PI is giving us the voltage VQ and VD. Now we have voltage VQ VD which are constant in nature. So as like it will tell directly, as suppose if you need higher torque, then VQ should be higher. If you need a lower torque, then VQ should be lower. So those are all constant terms. But as we know, this VD and VQ, those are the virtual voltages. Those are the virtual voltages of virtual modeling of the motor in rotor frame of reference. So in reality, those VT and VQ can't be applied to actual motor. So what is next? Definitely, when we want to apply those voltages to the actual motor, we need to convert those VD and VQ to VA, VB and VC. And as I said earlier, this VA, VB, VC is the output of this inverse Clark power transformation. So this VA, VB, VC, analog in nature, we need to convert into PWM. Those PWMs will be given to the inverter, and the inverter finally will drive the BLDC motor. So this was in short the FOC architecture for the BLDC or PMSM motor, and also as I committed earlier, we'll discuss about the torque control mode and the speed control mode. So in torque control mode, as we've seen, normally most of the EVs which are controlled manually, which are controlled with acceleration pedal and throttle, are always in torque control mode. So they receives inputs from the acceleration pedal, and then the further processing will be happening just like we are normally. So it receives the torque reference. But the next is another is a speed control. This is normally not used in general EVs, but if you go for some autonomous vehicle, where we want to control the speed of the vehicle as per the given commands, then in that case we are not giving inputs through some throttle. We are providing some profiles of the voltage, profiles of the speed, or we want to give some reference speed. Just like I heard in one of the electric bike, there is a one cruise mode where we are not giving inputs from the throttle. We'll just fix a particular speed and vehicle will follow that particular speed. So in that case, it is in speed control mode, not into the torque control mode. So when you control the throttle, it is a torque control mode, and when you given some reference of the speed and the vehicle supposed to follow the reference speed, just like in this case is the omega mr, omega normally represents the speed term, then that is called as a speed control mode. So over here, one more extra block will come into the picture, that reference speed is subtracted from the omega estimation. What is omega? We calculated from the motor, which is in feedback, and this is actual omega of the motor, actual speed of the motor. This is the reference speed. The error is calculated. Through the error, it is given to the PI, and the output of the PI is the reference IQ, or we can also call it as a reference torque, because as we said, the torque and the IQ are proportional term. IQ represents IQ is proportional to the equivalent torque of the motor. So this is IQ reference. So this is reference torque, and then again this further part is same as that of which we discussed earlier. So we saw the speed mode control, we saw torque mode control, we saw the requirement of IQ and why this transformation required. So because of this FOC, this transformations FOC can able to control properly, even though we have a non-linear nature of the voltages and speed, right? So that's all for today. Thanks for your attention. Thank you.